Moving on from linear models, and we'll be talking about nonlinear models. In particular, today we'll start with decision trees and some generalizations called bagging and random forests. And as the next few lectures progress, we'll go into increasingly more sophisticated nonlinear models, culminating with deep learning. Just a few announcements. Homework 2 is due tomorrow. Homework 3 will be easier than homeworks 1 and 2 in terms of the machinery needed to get things working. And mini project 1, which will happen after homework 4, is a casual competition where the class will go through this process of model selection, cross-validation, making sure you're not overfitting, and submitting a model onto a leaderboard in this case for a competition. In the case of the Kaggle project, the majority of the grade is in the process, how you actually go through the process of selecting a model for committing to the competition, and then a small piece of the grade is on how well you do in the competition. So for those of you who are obsessed about getting really, really high grades, don't fret. You can do really well in that mini project without being number 1. And for those who really want to be number 1, go nuts. Okay. Any questions about the logistics of that? Okay. So I thought it would be good at this point to sort of take a step back in the topics of machine learning that we'll be covering in this class and try to paint a picture of the broad landscape of the topics. So on the top I put supervised learning, on the bottom I put unsupervised learning. And most of this class indeed is about supervised learning. There'll be a small portion on unsupervised learning. And within those broad categories, which typically define the loss function, we have a bunch of other decisions that we need to make and that we'll go over throughout this class. Some of this we've already covered. For example, the choice of models. You can do linear or nonlinear. I think at this point we're basically done with linear models, unless you guys want to hear more about linear models. But we'll talk about nonlinear models starting from this point on. We talked about issues such as overfitting, the bias variance trade-off. How do you tell if your model is actually learning something that generalizes beyond its training set? So everything, including overfitting, cross-validation, sort of falls into this bucket. The choice of loss functions, we talked a lot about the choice of loss functions, how they have different behaviors, different characteristics, and oftentimes different interpretations. And that'll be a recurring theme moving forward. I may not emphasize all the multiple facets as much in the future lectures, but that's definitely going to be a recurring theme as the class progresses. We talked about learning algorithms and optimization. I would say that this week's lecture notwithstanding, this lecture and the next lecture next week notwithstanding, the learning algorithm of choice is stochastic gradient descent, but it's good to understand that there's an optimization problem and from which a learning algorithm is developed to solve that optimization problem. The final piece, which we only just very briefly touched on when we talked about logistic regression, is on probabilistic modeling. So that is, how do you actually model entire distributions of concepts? This is useful for things like generation. Suppose I train a model on a data set of faces, and I want to have this model, if this model has captured the distribution of faces, then I can sample from this model to generate new realistic looking faces. This is something that you've probably all seen in the media. They're called deepfake. They can do videos now as well as voices. And all of those capabilities stem from an area called probabilistic modeling, where you're trying to build this probabilistic model that captures a distribution of objects. And so we'll be talking about that for about a week and a half, 3 lectures in this class later on. And in fact, that'll culminate in a mini project where you have to generate your own poems from a training set of Shakespearean sonnets. Any questions about the overview of the topics in this class? Okay, so to the extent that this class shares significant overlap with CS156, that overlap is done. Okay, so this lecture, we're going to focus on nonlinear model classes. And in particular, we're going to focus on achieving the highest possible prediction accuracy So again, in this lecture and the next 3 lectures, so the next 4 lectures total, we will be focusing again on supervised learning, and our goal is to get the highest possible prediction accuracy that we can. And to do so, we need to go to nonlinear models. So these include, in this lecture, decision trees, bagging, and random forests. In the next lecture, I'll talk about boosting and some other methods. And then the next 2 lectures after that will be about deep learning. Okay, decision trees. So decision trees are, at the core, extremely simple concepts. Of course, they get scaled up into something that can become very complicated. But at the core, it's an extremely simple concept, and it's very simple to explain. So we'll do so via an example of a very simple decision tree. This is a binary decision tree. It's called binary because every node in this tree has 2 children, and therefore it's a binary tree. Okay, so if this looks like it's almost too obvious or too simple to be true or to be believable, it is not. It is literally what it looks like. Don't overthink it. When you make a decision, you have the root node, you have the internal nodes, and then you have leaf nodes. And the leaf nodes are where the classifications are. So in this case, I've used the notation 0 and 1 for the classification. Some people use -1 and 1. It doesn't really matter. So every internal node has a query, and I'll just call it Q of X. So X is the input features. And the query is a yes-no query function. Every leaf node has a prediction. In this case, because it's classification, we'll say it's 0 or 1. And the prediction starts at a root node. So let's say this is the input. The 2 features are male or female, and age greater than 11, or sorry, just an age feature, excuse me, in this case. So we first checked, so the query in the root node, which is also an internal node, in this case, checks the gender feature, and then it's a binary query, yes or no. So now we go down the node branch to the child node, which now has a query. Is the age feature has a value greater than 11, yes or no? In this case, it's yes, and so we predict a positive label in this case. So that's how a prediction happens. So given a decision tree, you simply walk down the decision tree from the root node through the sequence of binary queries associated with each internal node until you reach a leaf node which has a prediction associated with it. It's that simple. So that's the prediction. Okay, so a decision tree is defined by a tree of queries, in this case binary queries. A binary query maps the input features to either 0 or 1. Again, I'm using the notation 0, 1. It obviously doesn't matter as long as there's a consistent binary interpretation of the outputs. So in its basic form, it looks like this. So it's an indicator function whether the D feature, so feature D, is greater than some threshold C. That's the basic form. And you'll notice that all of these queries only look at a single feature. Right? So they only look at one feature at a time. So feature 3, feature 1, feature 55. And so what that means is that the decision boundaries that a decision tree represents, the decision boundary is this axis-aligned zigzag. So it's best shown with a picture. So this is, imagine we have a 2D training set. Here it is, positive and negative examples. And since it's 2D, there are 2 feature dimensions, the horizontal dimension and the vertical dimension. So let's start with splitting the vertical dimension. So now, everything over here answers the query positively and is in this child of the root node. Everything over here answers the query negatively, let's say, and in the other child node from the root node. We can then keep splitting and growing the decision tree. And now each of these partitions correspond to the data that gets routed to the leaf node. And then we can make a prediction, right? So every leaf node is associated with a prediction, and we can measure the accuracy of these predictions on the training set that we've collected. So pictorially, at least in 2 dimensions, this is what a decision tree looks like pictorially.
And the negative or positive label just corresponds to the 0 or 1.
Yeah, so for example, if this was a training set, so the question was, how do we decide on the labels? So I'll go through it more formally in a few slides, but if you look at this example, if this was our decision tree, then in this leaf node, so if, you route this query, it routes here to this side, and then this is the next query, this is the boundary of the next query, it routes to the left side, this is the boundary of the next query, it routes to the right side, this is the boundary of the next query, it routes to the left side, and in this leaf node, most of the training data that routes to this leaf node are negative, so I'm just going to predict negative. I'll make this more formal in a few slides, but that's the intuition. Okay, so what is the decision tree function class? So we talked about model classes and function classes, throughout this class. And again, I'm referring to model class and function class interchangeably. I don't distinguish between those two vocabulary terms in this class. So a decision tree function class is the class of piecewise static functions. So all possible partitionings over a feature space. And within a partition of that partitioning, the prediction is constant. In other words, all of these partitions are aligned with some axis of the feature dimension, of the feature space, and there are no, in other words, there are no diagonal boundaries that partition the data. All the boundaries are axis aligned. Okay, so clearly this is a nonlinear model, right? This type of classification boundary is clearly nonlinear. You cannot model this using a single line. Right? So you can create examples where even in 2 dimensions, there is no way for a linear model to achieve perfect classification accuracy or 0 training error. But of course, we can create a very simple decision tree in this example that can get perfect classification accuracy. And they can be, non-intuitive, right? So here's an example of another trick, just a toy example I made up, where for whatever reason the vertical dimension doesn't matter. There's no variability in the training data along the vertical dimension, but I can still create a decision tree that only splits along the horizontal dimension so that can get perfect training accuracy. As long as you don't have a negative point and a positive point completely superposed on top of each other, you can always get perfect training accuracy if you grow your decision tree big enough. Okay, well, there are some trade-offs, right? So, for example, suppose this is our data set, and you could easily model this with a single line. But for a decision tree, it's going to look a bit awkward, right? It's going to look something like this on the right. And to the extent that you have parts of your model that are doing things that are kind of useless. So, for example, this part of the boundary is actually splitting between a positive example and a positive example. Seems like a wasted boundary, but you need that because of the way that the decision trees are defined. So it can be awkward to model things that look highly diagonal. Here's a more extreme example. Okay, so at a high level, I think it's quite clear to see that if you let a decision tree grow in complexity, again, they can get very big. They are more accurate than linear models, certainly on the training set. And of course, you need to care about overfitting, but in practice, they typically are much more accurate than linear models. The linearity is often very important because the boundary that can accurately separate out the positive and negative classes tend not to be linear. The catch, of course, is that you need more data. Right? To learn these high-capacity models, you need more training data. And we'll talk about this more throughout the lecture. Here's a actually very small real decision tree trained on some biomedical data. This is actually very small. The real decision trees can get much, much, much bigger. But this is a real decision tree. Any questions before I talk about training? Yes.
On the last slide. So I guess in terms of training data, how much more do you need? How does it scale with this nonlinear model versus a linear?
So the question is, how much more data do you need? It's a great question. In general, it's hard to answer for sure. That's what people do for cross-validation. As a rule of thumb, I think for modern data sets, unless your data set is super simple, you should just try decision tree. Yes, question?
So I was wondering, when you mentioned that decision trees can't classify technical factors well, is it possible to do something like a change of basis, like a physical an analysis to avoid that?
Only if, the question is, can we do a change of basis so that the axis-aligned boundaries are less awkward? Only if that change of basis is uniform across the entire input space. If there's a single change of basis such that the entire space becomes more easily categorized using axis-aligned boundaries, then yes. Typically, that's not the case. Yes, question?
Won't such a change of basis be data smoothly?
Change of basis is not necessarily data smoothly. You could do an affine transformation, which actually preserves all the geometry. Any other questions? Yes?
How do you find which questions to ask?
Okay, so the question is, how do you find which questions to ask? That's basically equivalent to saying, how do you train a decision tree? So we can talk about that next if there are any other questions. Okay, so now let's talk about how do you train a decision tree. So imagine you had a training set, in this case supervised. How do we train a decision tree? So there's a few things to first understand conceptually. Every node in a decision tree corresponds to a partition or a subset of the training data. Every layer of the decision tree corresponds to a complete partitioning of the training data. All the children nodes of a parent node correspond to a complete partitioning of the training data associated with the parent. So for example, the root node is associated with the entire training set. The children of the root node form a complete partitioning of the data associated with the parent node. So in this case, since the parent node is the root node, the children, the first layer of the decision tree below the root node, corresponds to a full partitioning of the training set. So every training example routes to exactly one and only one of the nodes right below the root node. And so on and so forth. This definition is recursive. So the first thing to understand is that for the purposes of training, the data training, you can think of the nodes in the tree as exactly corresponding to a partitioning of the training set. So here's a thought experiment. Suppose we had a decision tree that was degenerate, just one node. So the root node is a leaf node. There are no internal nodes. Okay. There are no queries. We could just only make a single prediction. What is the prediction that maximizes accuracy? It's the majority class. In this case, there are 4 1s and 3 zeros, so we're going to predict 1. That's the prediction that maximizes prediction accuracy because that's the only thing we can do for this model, because it's only a decision tree of size 1, which is equivalent to just a bias or offset term. Okay, which means the entire training set corresponds to a single leaf node, which means we're only allowed to make one prediction. That's it. So this is a trivial decision tree. So the simplest decision tree is just a root node, which is also a leaf node in the simplest case, corresponds to the entire training set, and therefore the only thing you can do is make a single prediction for everything in the training set, or the entire input domain of the feature space. Which means we just make a single prediction of positive in this case, because there are more positives than negatives in this example. Okay, so what if we have 2 levels? Now we covered the case of just 1 level, which is a super degenerate case. Now let's look at a slightly more interesting case where we have 2 levels. So the root node has 2 children, which means there's a single query that we can place in this decision tree. So we have 3 decisions. We have what is the query, and what are the predictions in the 2 children nodes that are now the leaf nodes. So one question to ask is, well, how many possible queries are there? So here's one way to think about it. We could write a for loop over all possible queries. We can, since it's over every possible, every query is querying a single dimension at a time, then we could just simply write a for loop over all possible queries, and consider splitting them. And the question is, how many choices are there? Can anyone guess how many choices are there in terms of how many times this for loop runs for? The length of this for loop? Yes?
Is it like n times d, where n is the number of training points and d is the number of dimensions?
Correct. There are n times d number of possible splits. So if you try a split if you try a threshold c and you wiggle it a little bit and it doesn't change the partitioning, it doesn't change the outcome of the decision tree training. So the number of possible splits that actually change the partitioning of the training data is on the order of d times n, where d is number of features and n is number of training points. I'm ignoring any off by 1 thing because I care more about big O in this case. So that's the number. So that's the size of the for loop, right? If you were to do the decision tree training, you would just write a for loop that looks at if you do the vertical dimension, you sort the data points by their vertical dimension value, and then you try the midpoint of the separator between every vertical feature values, and then you compute the splits, and then you compute how good that split is, which is what we'll talk about next. But that's the basic idea. Yes?
Do you really sort them along all d dimensions?
So the question is, do we really sort them along all d dimensions? That seems really slow. Is that the idea, or?
Yeah.
It is really slow. It's not that slow. I mean, so the thing is, okay. Let's see here. The thing is, once you get, let's say we're going to do this recursively, right? And we're going to split this again. And assuming this is a balanced tree, it doesn't really matter if it is or not, but this only has half the data. This only has half the data. Right, so if you split the nodes here collectively, they only have n data points. So it is slow. It's not as slow as you might think it is, because the number of data points per level is conserved. Now, if you start having partial, this one has half of one data point, this one has half of the same data point, which happens sometimes in some extended versions of decision trees, that gets really slow, because now the number of data points grows exponentially as the number of levels, layers of the tree grows. But in the case where you hard assign, hard partition data points to one of the leaf nodes, one of the children nodes, excuse me, then the number of training data points is conserved as you grow the tree, which means it's not as slow as you might think it is. It's still slow. There are people who have proposed methods where you only look at a subset of the thresholds. So maybe not every data point, maybe every 10 data points or 50 data points. there are very many natural tricks you can do to speed it up, which you can imagine doesn't actually change the accuracy that much, right? But that's beyond what I'm going to talk about in this class. But there are ways to speed it up. Okay, so those are the total number of unique splits that we can make on a decision tree on a pre-collected finite training set. Now let's talk about how we can compute how good any particular split is. And in the decision tree literature, they call this measuring how good a split is using what they call impurity. And impurity is basically a loss function. They just, since decision tree people came from or decision trees originated from a slightly different community that then we adopted within machine learning, they use a slightly different vocabulary. But you can just think of this as a loss function. One such impurity is 0-1 loss. So let's start there. The 0-1 loss of a training subset, so S prime here corresponds to a subset of the training data. It could be the entire training set, or it could be just a partition of the training set. At this point, it doesn't matter. What the impurity says is that we're going to pick the label. In this case, we're just assuming everything's binary. And then we look at the disagreement of the data points in this subset with that label. And we're going to pick the one that has the lowest impurity. So this basically corresponds to saying, I'm going to predict the majority class, and I'm going to measure how many data points disagree with the majority class. So if in this subset it's 55% positive, 45% negative, then I'm going to predict positive, and 45% of the data points in this partition disagrees with me. So the 0-1 loss is 45% times, I guess, times the number of data points. Okay, so for a single root node, for a decision tree where there's a single node, the root node corresponds to the leaf node. We just predict the positive class. The impurity is 1 because there's one negative example that disagrees with the majority class. We can split it. So we're gonna run a for loop that considers all possible splits. So here's one possible split, and we'll compute the impurity. And again, the impurity in this case, since it's conserved, everything sums over the training set. You can just sum the impurities of the two new children nodes compared to the impurity of just the root node. And the impurity here is still 1. So the impurity reduction is 0. There's no benefit from making this split under this particular impurity measure. Okay, let's start again. Let's try this split. Okay, the impurity of the sum of the impurities of the leaf nodes, the children leaf nodes is 1. It's the same as just having the root node. So the impurity reduction is 0. Okay. So if we happen to get this split, which is one of the splits that we will eventually loop over in our for loop, we'll see that the sum of impurities of the children nodes is now 0, which is a reduction in impurity compared to just having the parent node. And this definition, of course, recursively applies as you grow the tree. Okay, so like I said before, impurity is basically a loss function. The goal is to train a decision tree with low impurity in the leaf nodes. So the sum of impurities in the leaf nodes should be as small as possible. That's the goal. So the impurity over the entire training set is equal to the sum of impurities over the leaf nodes that partition the training set. So you can just write it like this. And then for each of these, for 0-1 loss, it looks like this. If your impurity measure is 0-1 loss, it looks like that. Any questions so far? Okay. So I'm going to come back to a problem with 0-1 loss. Some of you probably have already guessed that 0-1 loss has a problem. So here's one example. And in this particular example, there's no way for a single split of the data to reduce the impurity to reduce the impurity from the root node. No matter what split you try, if you use 0,1 loss as your impurity, all the possible splits leads to an impurity that is the same as having not done the split at all. In other words, all partitionings of the parent node, in this case just the root node, give the same impurity reduction of 0. Okay, so this is basically just another way in which the flat and discontinuous aspects of 0,1 loss sort of presents itself again. So for stochastic gradient descent, we know that the 0,1 loss is flat and discontinuous, flat or discontinuous everywhere, so that there's basically no training signal in it if you're not, so you don't know how to make progress. That is basically in a nutshell what's happening here, just in a different format. For example, if we made this partitioning, we have not improved the classification accuracy because we're still going to get one wrong. So 0,1 loss is not improved. But this particular split will lead to another split down the line that will improve the classification accuracy. So we need some smoother measure of impurity than 0,1 loss in order to make progress in this type of top-down decision tree growing, where you only look one step ahead when you grow the tree. So there are many other impurity measures people try. Some people want something that's a little bit more continuous, a little bit more smooth. One simple one, which is very simple to explain, is Bernoulli variance, unnormalized Bernoulli variance. So the impurity measure of a partition of the training set, S prime, is equal to, so let P of S prime denote the fraction of S prime that are positive. Right, so the variance, if you know about Bernoulli random variables or Bernoulli distributions, you know that the variance of a Bernoulli, you can think of the training data in a partition as being Bernoulli distributed, so either +1 with probability of P, 0 probability 1 minus P, and the variance of this Bernoulli distribution is P times 1 minus P, which is just this. And then since we wanted this thing to have a scale equal to the number of training examples, we multiply by the size of the partition. And you can check that this is equal to number of positives times the number of negatives divided by the size. Okay, so it's also easy to check. Let me just pull up this guy. That the worst impurity is when the fraction of positive and negative is exactly 1/2, and the best impurities are when it's all 1 or all 0. And so the impurity function looks like this. So if you try to reduce impurity with this, if you try to train a decision tree whose leaf nodes have the lowest sum of impurities, then this is going to prefer leaf nodes that have almost all 0s or almost all 1s in that partition to that leaf node. But of course, how much it prefers that is a smoothly varying function of the fraction. Yes, question?
Why do I want the purity to be symmetric with respect to the number of positive and negative values?
Okay, so the question is, why do I want the purity to be symmetric? That's a great question. I should give you a cookie. That's the first time someone's ever asked that question in 6 years of teaching this class. You don't necessarily want it to be symmetric if you care more about the positive class than the negative class. So you can wait, It
seems like I can make a better decision about how to move my split if it was not symmetric.
So in general, you're saying that in general you can make a better decision how to move your split if it's not symmetric?
Yeah.
I don't know if that's true. I think you'd only care about this if somehow the positive and negative classes have different meanings. Like positive is cancer and negative is no cancer. They have a very asymmetric cost in real life.
Okay.
I don't know if it'll actually I don't know if it'll actually give you a benefit in terms of algorithmic improvements in terms of training.
Okay.
Okay, so let's go over how to, this simple example again, but using Bernoulli variance as the impurity measure rather than 0-1 loss. This is the impurity. This is the, impurity, and then if we split this, the sum of impurities is smaller, so 1/2 is smaller than 5/6. And then if you try this split, the impurity also reduces. 3/4 is also smaller than 5/6. So here, again, in the extreme case, in the naive case, we run a for loop over every possible partitioning. Of course, in practice, you may want to skip some, but let's just say we run a for loop over every possible partitioning. So here's 2 that we ran over, and you can see that they both have impurity measures. With the children nodes, their sum of impurities is smaller than the impurity of the parent node. Of course, we're going to choose the one that has the highest reduction in impurity, which is this guy. Yes, question?
When you're looking at impurity reduction, do you generally only look at horizontal axis, like the vertical axis, or do you switch between the two? Or
Okay, the question is, how exhaustive do we look at this before we make a decision? And the answer is, in the naive case, you look at all axes, and then you choose the best one. Okay. So, you can think of, in the case of Bernoulli variance, you can think of each partition as encoding a Bernoulli distribution over the output variables, the binary class, right? And the distribution, the expected value of this random variable as exactly the expected value of the number of positive versus negative examples in that partition. And the goal is to figure out a way to partition the space using a decision tree in this case, that's axis aligned, where the partitions, individual partitions, have low variance. That's the interpretation. There are many other impurity measures. One very popular one. So the Bernoulli variance actually is not the most popular impurity measure. It's just the one that's easiest to explain. There are many other ones. There's entropy, which looks like this. I should mention this is unnormalized entropy, so we're not dividing, so we have to multiply by the size of the training set, or the size of the partition. It's also known as information gain, for those of you who know something about information theory. There's the Gini index, which looks like this. One thing to note is that they all kind of look the same, right? They all kind of, the shape varies a little bit, but they all sort of have the same shape to a first order approximation. And that's more or less, that's not a coincidence, that's basically intentional. So the Gini index and entropy are the two impurity measures that are more popular and the ones you'll find implemented in many machine learning packages. Yes?
So is the intuition by the reason you don't normalize because you only have a finite number of layers? So if you have a bigger, subset in one partition, you should care about the error just as much because.
Right. So the question is, So the question is, why is it unnormalized? So the impurity score of this partition has twice the meaning of the impurity score of this partition, because your training loss is summed over every example in your training set. And so whatever impurity you measure here should have twice the weight of the impurity you measure here. And one way to achieve that is to just keep everything unnormalized, which means you just multiply these things that depend on fractions by the size of the data set you're computing the fraction of.
And so if you were allowed to have a larger subtree on one side, a larger data set, then you might want to normalize, or would it?
No, you care more about that.
Okay.
So like, this is a good split. This is a good split because it shaved off 2/3 of the data set, and I mean, this is going to give you let's see here. This is going to give you an imbalanced tree, right? Like the left child has depth 1 and the right child has depth 2, or the left branch has depth 1 and the right branch has depth 2. It's not a balanced tree, and that's totally fine. Yes?
So is it just like more algorithmically efficient to use some loss that's not the 0-1 loss? Because like if we just looked, you looked at like the next two splits, we could come up with something that has like a loss of 0, right? Using the 0-1 loss. Is it just that?
Yeah, it's a bit hard.
Is it just that using another one allows you to like make decisions about how to grow your tree with less splits?
Finding the optimal decision tree with 0-1 loss is a bit hard.
Okay.
Which means if you can solve that, you can solve lots of interesting problems. Which is why people use these surrogate measures that do one step look ahead when they grow the tree. Finding the optimal linear model in terms of 0-1 loss, I believe that's also NP hard. Which is why people use hinge loss and log loss and then do gradient descent, which is like one step look ahead. Okay, so yeah, in conclusion, all the good impurity measures look quality the same. They give you a handle on how to greedily grow this tree with one step look ahead procedures. So let's just formalize what that looks like. So you all hopefully have an intuition of what the training algorithm looks like. I'm going to present it to you more formally now. So the algorithm works as follows. It's called top-down training. The name is exactly what it sounds like. The name implies exactly what it sounds like. We're going to recursively choose the split of a current leaf node with the greatest impurity reduction over all possible splits until some stopping condition is met. Okay, so step 1. We have just the root node singleton as a singleton node in the tree, which means it's also the leaf node. We predict the majority class. It has some impurity measure. Step 2, we loop over all possible splits of the entire training set, and then we compute the impurity measures of the resulting children nodes. So now these are the leaf nodes, and we commit to the one that has the greatest reduction in impurity. In step 3, we loop through both of these leaf nodes over all possible splits of both of those leaf nodes and look at the one that has the greatest reduction in impurity. So we'll try this one, we try this one, and then we sorry, we actually looked at numbers. Try this one, and then we try this one, we commit to one, and then we do that. And then we just keep doing that until some condition is met. So the reason why you want it to be unnormalized is that as you now look to split as you look to split a node that is currently a leaf node of a part of a bigger tree, you need a way to compare apples to apples of splitting this leaf node versus splitting this leaf node. And if this leaf node has much more training data, a small impurity reduction here could be worth a big impurity reduction here where it only has a small amount of training data. So that's what this loop looks like. That's what this loop says. I'm going to loop over all the current leaf nodes and then I'm going to compute the best possible split. Yes, question.
I'm a bit confused about this looping over all possible splits. Like if I have a real value feature, how do I loop over all possible splits?
Well, because you have a finite training set, there's only a finite number of splits that matter. The ones that bisect 2 data points. And the number of splits that matter is equal to, sorry, oh my god. Sorry. D times N. Nope. If I have a continuous feature space, only 5 data points, there are only 4 splits that matter.
Okay.
I mean, sorry, order B times N. There's an off by 1 here that I'm ignoring. There's only 4 splits that matter. Question, yes?
The topmost node, we start with like gender, but like we start with like age, and then that's
I'm sorry, I didn't
like
hear.
what? I guess my question is for deciding like which to do for the top node, like in our loop, potentially could be about over age as well to determine the loss is higher.
Correct. So let me go over the example. So at this point, we loop over both features. In this case, in this particular example, gender and age, and then we commit to the one that has the greatest reduction in impurity. So we looped over both, and then we commit. Let's say we committed to gender. Maybe we committed to age if it was a different data set. Okay. So that's basically how decision tree learning works. The process is called top-down induction or top-down training, depending on who you talk to. So first you look at all the splits on both leaf nodes over both dimensions. So we're trying all possible splits. I'm skipping many, but I'm trying all possible splits of both the leaf nodes. I also spent a long time on these slides. And then we commit to one, so we committed to that one, right? And now then we can, let's just say we skipped a bunch of steps and we committed to the best possible split of the bottom leaf node as well. And then that process continues until we've got this tree. Okay, some properties of top-down training. Every intermediate step of this process is a decision tree, is a valid decision tree, which means you can stop any time and you have a model. Top-down training is called a greedy algorithm in the sense that it doesn't backtrack. Once you commit to a top-level split, once you've already committed to that, you don't look back. You just keep going. Okay, so the last question is when to stop. Here is the same training data and 2 possible splits of the 2 possible decision trees. So the left tree is a subtree of the right tree. So the right tree you just kept going, and the left tree you stopped earlier. Now the right tree has lower training error, has lower impurity. Well, the key question is, doesn't it have lower test error? Because that's what we actually care about. Right. So in general, assuming you don't have degenerate points where a positive point is exactly superimposed on a negative point, if you keep running your decision tree training algorithm, you will perfectly classify the training set. You will get 0 impurity. I think at this point we all have the suspicion that such a decision tree that has 0 training error is probably overfitting to the training set. I mean, just look at this tree on the right, right? What's going on here, right? I mean, this is probably overfitting happening right here, for example. In general, of course, it's high dimensional and it's hard to visualize. Okay. So how do we figure out where to cut off the training so the tree doesn't get too big and too complicated? In other words, how do we regularize? Okay, stopping conditions. So, minimum size. Do not split if the resulting children are smaller than a minimum size. And here size corresponds to the size of the partition of the training data that partitions to this child node. Maximum depth. Do not split if the resulting children are beyond some maximum depth. Maximum number of nodes. Minimum reduction in impurity. Do not split if the resulting children do not reduce impurity by at least some percent. You know, these are all valid. I think minimum size is the most. I think minimum size is probably the most popular one, or maximum number of nodes. So the first one and the third one are the most popular. If you look at your machine learning decision tree learning packages in Python, they'll have a flag that says what stopping condition you want to use. You just pick one. It's a pseudocode. I won't go over any detail. If you want to look at pseudocode, this is what a pseudocode looks like. Let me talk about, for a minute, classification versus regression. In classification, the leaf nodes are 0 or 1. We're not loss of generality. You can do -1 if you want. Okay, it doesn't matter. In regression, the leaf nodes are real value. In classification, the selection of the label is the majority class. In regression, it's the average of the labels in the leaf node. Both are piecewise constant function classes, because they just predict a single number in the leaf nodes. In classification, the goal is to minimize 0-1 loss. In regression, the goal is to minimize squared loss. In classification, because 0-1 loss is flat or discontinuous everywhere, we instead use an impurity metric based on that's smoother, right? Based on some fraction of positive or negatives. For regression, this is actually much easier. We can just actually set the impurity as squared loss, and that just works. Yes.
So when I'm placing my splits during training, do I always pick like the midway between the 2 points that I would be splitting with that?
Yes, you have no reason not to pick the midway.
Okay.
Yeah. Okay, so just to recap, decision trees, you train top down, minimize some notion of impurity, which is equivalent to some notion of training loss, until some stopping condition is met. Find that the optimal tree is retractable, because it's you can show that it's a V-hard. Decision trees can be thought of as piecewise constant function classes. They are nonlinear, and all the pieces are defined by axis-aligned partitions of the feature space. They're typically much more accurate than linear models if you have enough training data. And this was the last point is perhaps something that is debated a lot in years past. These days, I think, unless you have reason to just want a super simple model, I think decision trees and neural nets are just my default for most generic data science problems. Any questions? Yes?
When you're classifying with 1 to 2 categories, is there anything more sophisticated than just like doing a binary classification?
For multi-class, there's a multi-class version of entropy, let's say.
And the algorithm is for training is much the same.
Yeah. It's exactly, you just predict the majority class, and your measure of entropy. That's the definition of entropy, and if you look at this is actually if you look at this this formula, it's just summing over the categories, in this case positive and negative, and computing the fraction. So computing the fraction let's say p is a fraction of positives. It's p log p, And then this P is the fraction of negatives, and it's P log P. So if you have multiple categories, you just sum over the total number of categories, and you get P log P, where P is the fraction of that category. So this generalizes trivially to multiple categories beyond 2. This definition. Yes?
So instead of doing like deterministic partitions of these sets, could I maybe use some fuzzy set theory and make like some fuzzy partitions of the sets?
You can. The problem is that the number of training examples grow exponentially as the depth increases.
Okay.
That's why people don't do it. Okay. In the remaining about 20 minutes or so, I'm going to talk about bagging. So, it's motivated by the bias variance trade-off. So let's just recap that first. So test error is the thing that we actually care about, minimizing. And it's basically a function of the true data distribution that is unknown to us. We assume that we have finite samples of training data from the test distribution, and then we train a model to minimize error on this distribution, on this finite sample. And if we think of the actual test error, so of a model that we train on a training set, it's actually the expected loss sample from the true distribution. So overfitting happens when the test error is much higher than training error. So we have this true distribution from which we sample the training set, and then we train a classifier on this training set, but we actually care about the test error, which is the expected error over here, which we don't have full access to. This is the recap of the bias variance decomposition. I won't go over it in detail, other than to remind you that for linear models, and let me just skip this in the interest of time. Let's go straight to this slide. So if you recall, this is an example where we trained a model on 7 data points sampled randomly from the test distribution, which are the red points. We trained a model, we computed its prediction, and then we repeated this process, I think 1,000 times. And then we plotted, in this case, the average prediction of a linear model, that's the black line, the average prediction of a quadratic model, and the average prediction of a cubic model. We also plotted the variance of a prediction of a linear model, which means the variability of the prediction within itself for both a linear, a quadratic, and a cubic. And the test error can actually be completely decomposed in the case of squared loss into the sum of bias squared and the sum of variance. And note that the variance term has no dependency on the actual label. The variance term only depends on the variability of the predictions of the model trained on random subsets of the test data. And no dependence on the actual label. Only the bias, in this case, has a dependence on the actual label. What that means is that even though on average the cubic function class models this data pretty well, the variance is so large of an individual model that it's likely to overfit to your training set that you collected if it's only a training set of size 7. So high variance implies overfitting, which means that the model class is unstable. Variance increases as your model class complexity increases, so the cubic model class is higher variance than quadratic, which is higher variance than linear. Variance reduces as you collect more training data. High bias implies underfitting. Even with no variance, even with infinite training data, or all the training data, the model class will still have high error, as is the case for the linear model class. Bias decreases with model complexity, and to a first order approximation is independent of training data size. So now let's talk about the bias variance decomposition, or think of the question, yes? Okay. Now let's talk about how we can think about this in the context of decision trees, right? So in other words, here's our training data, here's the splits we made. What we care about is the test data. So here I'm just plotting a bunch of other data points that form the test distribution. And we care about the error on the test data. That's what we actually care about. So decision trees, at least the full decision trees that can get very deep, are low bias, high variance models. Highly nonlinear, very easy to overfit. Different samples of the training data as a thought experiment, if I plug this data again from this distribution on a different sample, they can lead to very different trees. And that's where bagging comes in. So the goal of bagging is to reduce the variance of a high capacity, high variance, low bias classifier. So in the ideal setting, we had many training sets. So imagine that we could just, imagine we had this thought experiment where we could collect the training sets over and over and over again. I'll call those S prime. We train a model using each of these training sets, S prime, and then we average their predictions. So this is just the formula. This is just a rewrite of the formula for the bias variance decomposition for squared loss. So we're doing regression here, but it's because it's mathematically simpler. So the expected error on any given test example as a function of the randomness of my training data that I've collected. So I have this process that collects training data randomly from the test distribution. So S is a random variable. The expected squared loss on any given data point, x comma y, can be decomposed into these two terms, where the first term is simply right. So z is the deviation, and so the first term, because the y cancels out, is the variance, and the second term is the bias. So if we sample multiple training sets, thought experiment, if we sample multiple training sets from the test distribution independently, and we have these multiple training sets of these multiple instances of this random variable of the training set, train a classifier or a regressor, average their predictions, then what happens? The variance will go down, and the bias is unchanged, right? So if we go back to this example, we'll get, if we were able to do this thought experiment, here I exactly did this thought experiment, where I repeated this process 1,000 times, and I computed the average prediction, and you get this black line, right? And then the variance scales down very rapidly if you're doing the average of 1,000 variables. Okay, and this process is called sorry. But suppose instead we do something else, because in practice this thought experiment is impossible to implement. In practice, typically we can't just go and recollect another training set from the distribution. So this thought experiment is impossible to implement in practice. So what we do instead is we sample an S prime from our S, our one realization of the training set. We resample it with replacement, and to get an S prime. So we resample S prime with a replacement from S. And this process is called bootstrapping. It's a very classical approach in the statistics community. It's been around for decades. And by the way, bagging is short for bootstrap aggregation. So we do this bootstrapping process where we have a training set S. That's the only one we have. We're going to create a bunch of virtual training sets by bootstrapping from it, which means sampling from it with replacement, to get a training set S prime of the exact same size as S. And because we're sampling with replacement, we're very likely to have duplicates of some training examples and leave out other training examples because we're sampling with replacement. And now we train a model on each of these S primes that was bootstrapped from the original training set, and we average their predictions. That is what bagging is. Now, the variance will go down slower than if we were able to do our pure thought experiment, because the S primes are no longer uncorrelated. They are correlated. But that's the idea behind bagging. If you have a high variance, low bias model class, and you want like a meta algorithm, so this is just like a wrapper around decision tree training. You could do this as a wrapper around any model class, but it works particularly well for model classes that are high variance, low bias. You basically resample your training set with replacement, and then with these new bootstrap training sets, we train a model, and then we just average all their predictions. Just like a 3-line wrapper around your original learning algorithm. So, bagging was popularized for decision trees, and so because decision trees at that time were the only high variance, low capacity, low bias model class that people used, and nowadays there are more. But here's how it looks for decision trees. You know, we have the original training set. We generate many bootstrap samples from that training set, which means we sample with replacement until we have a training set S prime that has the same size as S. We train a high variance decision tree on S prime, and the final prediction is the average prediction of all the decision trees that we've trained. That's bagging. Here's an experiment. This one's from actually many years ago now, where because of the way they set up this experiment, they can actually measure the bias and the variance. And there's there's 3 different approaches that they tried, and you can see that the variance decreased a lot if you do bagging versus just a single decision tree.
What does it mean to take the average of a decision tree?
You take the average of the predictions.
Okay.
Even though the prediction is binary?
Yeah, I mean you could always do voting. So I mean, yeah. So it's like 95. If you have 100 trees and 95 predict positive and 5 predict negative for this data point, you can just predict the majority class, which is positive. The theory of bagging work is easier to talk about for regression, in which case you actually just predict the average. But for classification, you just do voting, majority vote. Okay, so just a little bit of theory. So why does bagging work? Well, we can define the ideal aggregate predictor. I'll call that H sub A, which is basically the thought experiment, right? So it's the average of a bunch of predictors that we train, and assuming we're able to draw independent training samples from the test distribution. So this is the ideal aggregate predictor. For any input X, you have a bunch of predictors trained from different samples of the training data from the test data. You train a model, and then you compute their predictions, and you average their predictions. So H sub S is a decision tree trained on S. So this is the ideal aggregate predictor. Of course, this is impossible in real life, but as a thought experiment, it's useful. So here's the analysis of the ideal aggregate predictor. This is the loss of the ideal aggregate predictor on a this is the expected loss of H sub S on a single XY pair, expected value over with the expectation over the randomness of the training data. So we'll just do a squared loss because the math is super clean for squared loss. I'm just going to do some just very standard stuff. So you don't get to follow this exactly. This is just the distributive rule, some reshuffling of things that are now random variables, so you can move those out of the expectation, using some inequality identity, and then just some other algebraic identities. So what you get is that the loss here, which is the expected loss of a single predictor. So if I were to train a single predictor from a single training set, this is the expected value of its loss on an XY pair. and it is always it is always greater than or equal to the loss of the ideal aggregate predictor. Again, this proof is actually very simple. It's just manipulation. It's just very simple manipulations of arithmetic and algebra. So even though it looks kind of messy, it's actually extremely simple. The key insight is that the ideal aggregate predictor improves upon the expected error of any particular individual classifier or model that you train if this inequality is large. So this inequality is always, this always holds as an inequality, as a greater than or equal to. It gets better and better if this gap is huge. And this gap is huge if H sub S is, intuitively, this gap is huge if the individual model from model class is unstable because of high variance. Bagging, on the other hand, you replace this quantity, which is the single inequality in that entire proof. You replace that inequality with this form, where now we're bootstrapping S prime from S, right? This is what's actually happening in bagging. And now bagging gives you a reduction in error if this inequality is true, and if this inequality is large. And most of the time that's actually true. But of course it's not always true. So this gives you one mathematical characterization of when you might expect bagging to help. All right, the last thing I'll talk about very briefly is random forests. So, random forests are an extension of bagging for decision trees. Again, the goal is to reduce variance. And bagging can only do so much because the only thing that bagging does is just resample the same training data over and over again, and at some point that asymptotes in its effectiveness. Random forest says, well, let's sample both data and features. There was a question asked earlier about whether or not we actually had to look at all possible splits of the training data. And the answer is, in practice, if you use random forests, the answer is no. You explicitly don't do that. So here's how random forests work. We sample a training set S prime from S, bootstrapping, just like in bagging. And then we train a decision tree. But at every node in the decision tree, we sample a random set of features from which we split. We don't look at all features. So if it's like a 1,000 dimensional data set with 1,000 features, we might randomly sample 10 to look at, to compute splits. And every time we recursively consider a leaf node to split into 2 more leaf nodes, we randomly sample a new subset of features. We train these decision trees with these random splits on random bootstrap samples of the training data. We train a bunch of these decision trees, and then we average their predictions at the end. And that's random forest. The reason why this intuitively might be beneficial is that by randomly sampling features, it further decorrelates the trees, right? You can only you can only reduce variance so much if your models are already correlated. So bootstrapping the data only gives you so much variability that you can reduce. If you also randomly sample the features, you get even more variability that you can then reduce by averaging. Yes, question?
When you say sample the features, this is like without replacement, right? Like as opposed to when you're sampling S prime.
Yeah, just like just a random set of features, yeah. Without, right. That's it. All right, so just to go over this, and well, I'm almost done. So we have the initial root node. We randomly only this is a very trivial example. We randomly decide only to look at age and not gender. And then we randomly decide to look at only gender again. Over here, we randomly decide only to look at age, and that's basically how it works. It just adds more variability to the trees, which means there's more variability that you can eliminate by averaging. Okay, so just to recap, random forests are an extension of bagging to sampling features. It is specific in this case to decision trees. This particular form of training doesn't work for other function classes. It's a tailor-made approach only for decision trees. But the basic idea is that you sample a training set S prime, bootstrapping from the original training set. You train a decision tree top down, and in every node during training, you only sample a subset of the features for splitting. That's the basic idea. Here's just an empirical comparison. This particular comparison compared a bunch of different data sets and a bunch of different models. I just want you to note that random forests are way up here. They tend to perform extremely, extremely well. Hint for the Kaggle competition. Any questions? Excuse me? Right. So I'm not an expert. I haven't read the entire literature, but I think the rule of thumb is something like square root of the number of features. So if you have 100 features, you randomly select 10. If you have 900 features, you randomly select 30. I think that's the rule of thumb that tends to be most popular. Of course, I'm happy to point you to resources that study this more empirically. I'm not an expert. Okay, so next lecture we'll be doing boosting, which is the flip side of bagging. We're going to look at high bias, low variance model classes, how to actually produce those with a wrapper script. And then recitation